Okay, so welcome back to the second talk of this morning session. We have Professor Xin Sun from Beijing International Center for Mathematical Research and Peking University. He will be talking about application of Liouville quantum gravity to the percolation. He's an expert in these topics. So it's Jenny to welcome Professor Xin Sun.
Okay. Thank you very much for inviting me to this very nice event. Today I will talk about the application of Liouville quantum gravity to 2D percolation. So here, two-dimensional percolation is only one model that I focus on, but there are more like models that we can treat. And the reason we focus on percolation is because this is simple to explain. So the model is following. So here we have a so-called side percolation on a triangular lattice, and the definition is that so we have a tiling of the hexagon of the lattice, and we color each hexagon with black or white with independent probability p, and this is a so-called Bernoulli side percolation with parameter p. And then so the question that people care about in statistical physics is phase transition, and percolation is a nice model to model the phase transition. And one of the canonical observable to look at in this model is a so-called crossing event. And the definition is the following. So we consider a topological rectangle, which is a Jordan domain with 4 boundary marked points. And then we consider the event that I have a y separating AB and CD. And this is a so-called left-right wide crossing event. And then we can ask what's the probability of this event depends on the percolation parameter P. And then, so as this side length of the hexagon tend to 0, Kasten showed that if this probability P is bigger than 1/2, recall that P is the probability that I color this hexagon white. And he showed that if P is bigger than 1/2, then this probability will tend to 1. And if P is smaller than 1/2, this probability tends to 0. And the so-called phase transition point, or the critical point, is when P equal to 1/2. So here he showed that this probability has a non-trivial upper and lower limit. And so further in physics, Michael Eisenman, he conjectured that this crossing probability actually have a scaling limit, and this limit should be conformal invariant in the sense that it should only depend on the cross ratio of these four points. Namely, so in order to compute the probability, we can first use conformal map to map this topological rectangle into an actual rectangle, and then try to compute the probability. And this probability was exactly computed in a paper by John Cardy in the following year. And so he uses the non-rigorous conformal field theory. This is the famous Cardy formula for percolation. And the two-dimensional conformal field theory is a class of quantum field theory with rich algebraic and geometric structures. And so there are two main motivations of conformal field theory from theoretical physics. One is the string theory and the two-dimensional quantum gravity, which corresponding to the mathematical, so in mathematics, that would corresponding to random surface. And the other motivation is this two-dimensional lattice models at criticality. And so interestingly, over the last, let's say 25 years, there is a subject in probability which complement this conformal field theory approach. This is a so-called two-dimensional random geometry. And here there are two key objects. One is the so-called SLD curves, and they describe the scaling limit of 2D lattice models. And the other is the Liouville quantum gravity, which is theory of random surface. So this slide summarizes the philosophy of how to use conformal field theory to understand lattice models. So what happened is that many two-dimensional lattice models, similar to percolation, they enjoy conformal symmetry at critical point. And so their partition function can be viewed as proportional to some power of the determinant Laplacian. And this power is related to a certain conformal field theory with the so-called central charge. And this conformal field theory would dictate the correlation functions in the model. And here, this is one of the most famous example called the two-dimensional Ising model. And for Ising model, the central charge is equal to 1/2. And for our case of percolation, the central charge is equal to 0. And then, so Ising model belongs to a family of CFT called minimal models. And this is the first family of CFT studied in this seminal paper by Liouville and Pollack of Zamologikov in 1984, which found this subject of two-dimensional conformal field theory in physics. And percolation, it also believed to be described as CFT, but it doesn't belong to this series of minimal models. Nevertheless, so without understanding this CFT fully, Cuddy was able to make the predictions based on some general principles of conformal field theory. For example, so he argued that this crossing formula for percolation, it can be viewed as some 4-point function of a conformal field theory. And then using this general philosophy BPZ, he argued that this crossing probability should be a solution to a second-order differential equation. And in this particular case, it's just the hypergeometry function. So, and this is the Cuddy formula. So the rigorous proof of so in the case of side percolation triangular lattice, so Smirnov rigorously proved the Cuddy formula. So and actually he proved something stronger. So for the time reason, so I will not give the detail of the statement of Smirnov theorem, but this theorem will imply Cuddy formula. And around the same time that Smirnov proved the Cuddy formula, there's another breakthrough in probability, which is Schramm's discovery of SLD curves. So what Schramm realized is that if you assume that in these two-dimensional lattice models, if you assume that there's conformal symmetry in the scaling limit, and you assume some spatial independence, then there's only a one-parameter family of random curves that can encode the information of the scaling limit of the lattice models. And this family of curves is the so-called SLD curves. And the parameter is usually denoted by kappa. So this provides another approach complementary to conformal field theory to understand the scaling limit of lattice models. And there's a dictionary between the CFT approach and the SLD approach, which is this relation. So the central charge of the CFT and this kappa parameter supposed to have this relation. We can see that percolation should correspond to SLD6, and the Ising model would correspond to SLD3. And both of these cases were established by Smirnov's breakthrough work and several follow-up works. But there are many other conjectures about other models. And okay, so combining the work of Schramm and Smirnov, we know that SLD6 should describe the scaling limit of percolation. And actually, to be more precise, so the SLD6 curve, it only describes the scaling limit of a single percolation interface. But if you consider a so-called loop ensemble variant of the SLD6, then you are able to describe the full scaling limit of all the interfaces between the white and black clusters in percolation. And the bottom line is that these convergence results, they reduce the understanding of large-scale behavior of two-dimensional percolation to the understanding of SLD6 curves. And this combined with these rich predictions from conformal field theory, this motivated the following class of questions, which is we know that so CFT enjoy very rich exact solvability, and this gave some conjectural formulas on the scaling limit of lattice models, such as the Cuddy formula. And this would, and then given the connection between SLD6 and the lattice models, this would also give conjectural formulas on corresponding SLD curves. So we have a large set of questions concerning SLD curves. And so in this point of view, the Cuddy percolation formula actually corresponding to a formula that the SLD6 curve hitting some particular interval. And these kind of probabilities are easy to compute using Ito calculus. If you are familiar with Ito calculus, and then you would be able able to find a certain martingale observable to compute this probability. And the fact, and this BPZ equation corresponding to the fact that certain functional is a martingale, and then there's no term in the second order, and that will give you a second order dependent equation. And so in Hardy formula, many BPZ inspired formula for SLE are derived this way. There's one thing I want to clarify, which is this argument does not provide the independent proof of the Hardy formula for percolation, because in order for this to work, we need to a priori know that the percolation on triangular lattice already converge to SLE6, and the proof of the convergence actually relies on Smirnov's proof of the Hardy formula. But once we know that the lattice model converges to SLE6, then once we have a formula for SLE6, we can say that the corresponding observable for the lattice model convert to this formula. And so another application of this perspective is the evaluation of the crossing exponent for percolation. And so here the picture shows the one of the most important exponent, which is the one-arm exponent. And so here we still consider a crossing event, which is the event that there is a white path crossing the inner boundary and outer boundary of the annulus. And then by conformal invariance, we know that the scaling limit of this crossing event should only depend on the ratio between the inner boundary and the inner radius and outer radius. And it's not so hard to show that the asymptotic as this ratio tend to 0 should behave as a power law. So there should be a power describing the asymptotic. What is highly non-trivial is that it's actually computable. So here the one-arm exponent goes to 5/48. And this was first predicted in physics, and there are several methods predicted. One of them is a CFT. There's also a quantum gravity method that I will explain later. And this was rigorously proved using the SLE6 method. And the idea is to realize this one-arm exponent as the leading eigenvalue of certain second-order dependent equation. And the similar thing, the similar exponent can be considered for other crossing events. So here we have a so-called polychromatic two-arm crossing event, which is an event that I have two paths, one white, one black. They both connect the inner and outer boundary of the annulus. And so more generally, we can consider the so-called polychromatic J-arm event. So here, polychromatic means that in the crossing color pattern, I assume that there's both white and black colors. And so then we can define this family of exponent called the polychromatic J-arm exponent. And again, in physics, it has been predicted that the exponent should be like this. And this was again rigorously proved based on SLE6 and Ito calculus. Okay. And okay, so the following formula is another prediction by Cuddy, which is asking about the precise crossing probability. So here we can see that both the one-arm exponent and the two-arm exponent is asking the leading asymptotic of this probability as this ratio tend to 0. But we can also ask what is the exact formula for this probability, similar to the Cuddy formula for the rectangle crossing. And here, Cuddy, he also have a similar, so he also have an exact prediction. And but instead of using the BPZ approach, he used something called the Coulomb gas method. And this method so far is still mysterious in mathematics. And this is the first result I want to present, which so far can only be used, so far can only be proved using the method of Liouville quantum gravity. And so the reason that it's not easy to use Ito calculus is because unlike the rectangle case, In the annulus case, we don't have a natural boundary marked point. And then it's hard to introduce the notion of time. And without the notion of time, it's not easy to use Ito calculus. And if you artificially use Ito calculus, so you would arrive at a second order PDE. And for second order PDE, we don't know how to write down the solutions in general. Here, so by the way, I want to mention that this function here is the so-called Dedekind eta function, which is a fundamental function in conformal field theory. It's the character for the Virasoro algebra. And there's a reason for it. Okay, so now let me start to explain this quantum gravity method. So I will first explain at the physics level how to use quantum gravity to derive this one-arm exponent, this 5/48. And so one way to rephrase a one-arm exponent is to ask, so let's consider a planar region with n squared vertices, and then I want to ask what is the size of the boundary connecting cluster. So here, a hexagon is on a boundary cluster if I can find this single color path connecting to the boundary. So here, I'm just counting how many hexagons are there in this pink region. And then just by this simple linear additive expectation, we can see that the one exponent equal to 5/48 is equivalent to the statement that this size of this boundary cutting cluster is of the order of n to the 91/48. So this evaluation of the one exponent is really just some enumeration problem, but this is a hard one. And the idea of using quantum gravity is the so-called Kisnik-Polyakov-Zamolodchikov relation. So the idea is that, okay, so in order to solve this more difficult enumeration problem, let me first switch to a simpler problem. So here, this is a percolation on the triangular lattice where I view every hexagon as a vertex, and then this is a regular triangular lattice. So now I drop the condition that every vertex has degree 3. So I just consider some uniformly sampled triangulation of a polygon. And then I can still consider side percolation on top of it, and then I can ask the similar question. So what is the typical size of this boundary connecting cluster? And it appears that on this random triangulation side, the enumeration question becomes simpler to answer. There are several ways to count the size of this cluster. And then, so what you would get is what I call the quantum exponent. This is something you can obtain using simpler combinatorics. And then what is magical about the KBZ relation is that this is an explicit quadratic relation between this quantum exponent and the final exponent we want to compute. So then if you are a physicist, just plug in this formula, you get the derivation of this one exponent based on quantum gravity. And so the KBZ relation was originally derived from the conformal field theory description of Liouville quantum gravity. And then, so around the same time, there are very advanced methods appeared to count the lattice models on planar maps using random matrix. And so by comparing nodes, this provides the verification of the KBZ relation at the physics level. And then in physics, this provides a powerful framework to study random fractals. And one of the most famous applications of this KBZ relation in physics is Bertrand-Duplantyer's argument for this famous Mandelbrot conjecture. So, so his conjecture says that the frontier of the planar Brownian motion has fractal dimension 4/3. And in a more elementary way, it says the following. So let's run a simple random walk until it hits the boundary of some box. And then suppose the box is n by n. Then the question is how many vertices are there on the boundary of this random walk? And this conjecture says that the size should be n to the fourth power. When Mandelbrot made this conjecture, he was mainly just based on some not very good computer simulations. And so the first convincing argument was made by Duplantier. And it was later, again, rigorously proved using the connection between S36 and Brownian motion. So the proof itself by Lawler, Schramm, Werner, it does not use anything about Liouville quantum gravity. But I think this argument by Duplantier is a huge inspiration for probabilists to really understand the mechanism behind Liouville quantum gravity and the CFT description of the Liouville quantum gravity. And the first work on this direction was by Bertrand Duplantier, collaborating with Scott Sheffield. So they laid the mathematical foundation for Liouville quantum gravity probability, and in that paper they have a first derivation. So they have a first rigorous version of the KBZ relation. Okay, so the next few slides summarize the mathematical framework for Liouville quantum gravity. So the basic input is a random function called the Gaussian free field. And in our talk, we would focus on Gaussian free field on a two-dimensional Riemannian manifold. And here, the definition of the Gaussian free field is just this random Fourier sum. And the Fourier modes is given by the eigenfunctions of the Laplacian operator on this manifold. And the Fourier series is just ID Gaussians. And so one subtle thing is that this convergence of the Fourier series, it only holds in negatively indexed Sobolev space. And you can also see it from computing the covariance of the Gaussian process. So the covariance would be the green function of the Laplacian operator. And we know that in two dimensions, it has a logarithmic singularity. So this means that this Gaussian free field in two dimensions is not a point as defined. In order to visualize the random function, what you can do is you can do some regularization procedure and then simulate. And then the Liouville quantum gravity with the parameter gamma is the random geometry given by the exponential of the Gaussian free field. So here, so the basic geometric data is the random area measure, the random boundary length measure if your domain has a boundary, and the random metric. So the formal definition of the random area measure is just given by e to the Gaussian free field times the gamma parameter. And as we see from the last slide, so this phi is not a pointwise defined function. So in order to rigorously define this random measure, we need to do this regularization and normalization procedure. And the well-posedness of so the fact that this definition gives you a non-trivial measure is guaranteed by this theory called the Gaussian multiplicative chaos. And for this to make sense and being non-trivial, we need to set gamma between 0 and 2. And this can be similarly done on the boundary if your surface has a boundary. And so for the random metric, you can do something similar by regularizing the Gaussian free field and taking some limit of the Riemannian metric, but this is more difficult. So in order to demonstrate how difficult this is, I should mention that these two papers are both the ICM best paper award. So the first paper is ICBS, the first edition, and the second paper is this year. So you will hear more about the second paper in Jason Miller's talk tomorrow. But we don't need the random metric in my talk. So I would just say that this metric can be constructed. Okay, so and then so here is the origin of the Liouville quantum gravity in physics, and the starting point is the seminal paper by Polyakov in 1981, and so Polyakov he want to understand the quantum gravity in some topological surface, and this is just the random geometry of a given topology, and so in two dimensions, we know there's this uniformization theorem. Then in order to study the random geometry, we can first conformally embed the random geometry into a fixed remaining manifold, and then the random geometry would be encoded by this conformal factor in this conformal embedding procedure. And then we can reduce the study of the random geometry to the study of this random conformal factor, which is a random function. And Polyakov argued that this random function, it is governed by a quantum field theory, and the action of the quantum field theory is a so-called Liouville action. So this is a so-called Liouville quantum field theory. And Polyakov also argued that this conformal field theory, this quantum field theory has conformal symmetry. So this is a conformal field theory, and this is a so-called Liouville CFT. And in recent years, Liouville CFT has been made, has been constructed rigorously using the path integral method. And this is also based on the so-called Gaussian multiplicative chaos, which is the ingredients we need to construct the random measure in the Liouville quantum gravity. And so the output is that it produced a variant of a Gaussian free field on each remaining manifold. Okay, so one thing I want to emphasize is that when we try to construct the random geometry of the Liouville quantum gravity, we don't have to require phi to be exactly a Gaussian free field. We just need it to be some function which locally have a similar regularity property of the Gaussian free field, because all the geometric construction are local. So this phi could be some non-Gaussian function, but locally it can be decomposed into a Gaussian free field plus some like a continuous function. See, this is fine. And the Liouville conformal field theory, on every remaining manifold, it produces some variant of Gaussian free field. And this is a history. So this first done in the Sapir case, and then it is extended to other remaining manifold. And according to this philosophy of Liouville, Polyakov, and Zamolodchikov, and so since this Liouville conformal field theory has a local conformal symmetry, there's a rich symmetry algebra called the Virasoro algebra. And then the representation theory of the Virasoro algebra would allow you to compute exactly the correlation functions and partition functions. And this has been rigorously carried out in the Liouville case. And the two landmark result is the so-called DUZD formula computing the three-point function and the conformal bootstrap, which compute the endpoint correlation function from the three-point function. And this is the content of the talk by Remy Rose on Tuesday. And this is also one of the best paper award this year. And for us, we just need to remember that Liouville conformal field theory, it produced some exactly solvable variant of Gaussian free field whose random geometry corresponding to this random surface coming from Polyakov's quantum gravity. Okay, so now, as I mentioned, so the idea of using a KBZ relation to compute a lattice model exponent is that we first replace the Euclidean lattice into the random lattice. And then, but what's the relation between the Liouville quantum gravity and this random lattice? So the relation is the following. So first, it was known by the work of Legault and Mirmont and many mathematicians that if you uniformly sample triangulation, then viewing this as a remaining manifold, then in the natural topology of matching measure space, this random triangulation, it has a scaling limit. And they can show that the scaling limit, it almost surely has a spherical topology. So then this is called the Brownian sphere. Okay. This limiting procedure has nothing to do with conformal symmetry. It's just viewing this random triangulation as some piecewise linear remaining manifold, and then consider the natural topology in the matching measure space sense. And then, the Polyakov's original idea in probability language can be formulated as follows. It means that if you conformally embed the Brownian sphere into some fixed remaining manifold, such as unit sphere, then this random geometry for this Brownian sphere, it will induce some random geometry on the sphere. And then this random geometry is exactly Liouville quantum gravity whose conformal matter is given by Liouville CFT on the sphere. And this parameter gamma in LQG is equal to this particular number. And then more specifically, we can, so the statement can be summarized as follows. So if we sample phi according to this recipe of Liouville conformal field theory on this Riemannian manifold, and we set the Liouville quantum gravity parameter to be this value, then if we consider the random geometry coming from Liouville quantum gravity as a metric measure space, this will be isometric to the Brownian sphere. And furthermore, if we conformally embed the uniform triangulation to the unit sphere, the random geometry here, if you induce the geometry to the sphere side, the scaling limit would be this random geometry on the sphere. And so Pollacco's picture has basically fully realized on the case of the sphere and the disk, namely the simply connected domains. So the first major breakthrough was made by Jason Miller and Scott Sheffield. So what they can show is that they can construct an explicit variant of the Gaussian free field so that the induced Liouville quantum gravity random measure space is isometric to the Brownian sphere. And by the way, this is also one of the best people awarded in the first edition of ICDS. And so later with my collaborators, we showed that this Miller-Sheffield variant, it agreed with the Liouville CFT variant on the sphere. And there's a similar story on the disk, except you need to add the boundary length. And so later, Nina Holden and myself, we showed that the scaling limit of the uniform triangulation under a certain discrete variant of the conformal embedding, it actually converged to this random measurement space. Okay. And then, so now this is the conformal field description of a Liouville quantum gravity for the similar connected domains. What about for higher genus for Riemann surface with non-trivial moduli? So here, let's first consider the simplest case of Brownian annulus, and then so similar to the sphere and this case, we can consider the random triangulation with the annular topology, and then similar in those cases, in the natural topology for the metric measure space, there's a scaling limit, and we call this random surface a Brownian annulus. And so we can either consider some random boundary lines or we can fix the boundary lines. But here there's a new question arise, which is we know that for the annular surface, the conformal structure is not unique. So then we also need to figure out what is the law of the conformal modulus if we conformally embed a random annulus into some fixed geometry annulus. And this is a new question. And here, there's also a very nice answer in physics, which is given here. So this is saying that if we fix the conformal modulus, the CFT description of this Brownian annulus is also given by the Liouville CFT. So you don't have to look like too careful about these notations, but this basically means that if you fix the moduli, then the random geometry on this Brownian annulus in this fixed moduli, after you conformally embed it to this fixed moduli annulus, then this is still given by this Liouville quantum gravity induced by the Liouville CFT on this annulus. But then if you want to compute the law of the modulus, you also need to, there's additional weight. And this weight is governed by another CFT. This is the so-called Bosonian ghost CFT. And this is a CFT with central charge -26, and its partition function can be computed. And for the annulus case, this is a partition function. And the mathematical version of this conjecture is given by this statement, which we proved with Morrison and Hume-Rennie. So here, the reason of having A and B here is because this version is with the fixed boundary length. And here, this version is, we have the random boundary lengths, but they are the same statement. And this is a special case of some general conjecture about the CFT description of Brownian surface on non-similarly connected surface. Okay, so so what's the relation between this and this annulus crossing formula for percolation that I mentioned in the very beginning? So the relation is the following. So here, in this slide, so I outline some general method to prove that to show that the random moduli for the Brownian annulus is given by this formula. So you don't have to look at the detail of this argument, but you just need to remember that this is a general method that one can use to compute the random moduli of a random annulus. And in this particular case, my random annulus is given by the scaling limit of triangulation, which is a Brownian annulus. And then, so actually in physics, they also have conformal field theory description of quantum gravity coupled with so-called conformal matter. And here in this coupling, so we just need to decorate another independent conformal field theory that is describing the matter field. And then the quantum gravity is modeled by random triangulation, and conformal matters are modeled by lattice model at criticality. And so this central charge, it determines this gamma parameter in this LQG geometry, and this describes the local geometry. But then this partition function of the conformal matter, this determines the law of the modulus. And then if we plug in this philosophy to the percolation case, we can view the conformal matter to be percolation condition with some annulus crossing event. So we can view this as the conformal matter, and then this crossing probability can be viewed as a partition function of this conformal matter. Then we know that if we consider Brownian annulus coupled with this conformal matter, the random moduli will be like this. And since we know how to compute the random moduli of the Brownian annulus and the Brownian annulus coupled with this conformal matter, just by dividing the two density of the random modulus, we can get a partition function, which is the annulus crossing probability. So this is the way that we obtain that formula. So yeah, and this is a general method that we developed in this paper, computing the random modulus for Brownian annulus, and we applied it to the percolation case in a follow-up paper with my students. So let me just remind you the formula. Yeah, the formula is here. And we can see that there are these dedicated eta functions popping up. And this is not a coincidence. We can also see that in this Brownian annulus. Oh, sorry. I should go to the. If you look at the random moduli, we also have some similar formulas. Yeah. So you can see that if you look at the partition function of the Gaussian free field, you have some eta function, and the ghost field have some other eta function. So basically, whenever you are dealing with some conformal system on the torus or on the annulus, then having these modular invariant things are natural. Okay. Okay, so this is a result that we obtained using quantum gravity that the physicists already predict in physics. And here, these are some applications where the physicist doesn't know the answer a priori, and we obtained using these methods. So here, we can equally naturally consider the so-called monochromatic arm events and arm exponents. So this is the example of the so-called monochromatic two-arm events, which is we just have two disjoint crossing of the annulus of the same color. And so this is equally natural as these polychromatic two-arm events. And then it's also not hard to show that there exists some arm exponent that describe the asymptotic as the radius ratio tend to 0. But surprisingly, even for the beta 2 case, this was only solved recently. And for the beta, for J bigger equal to 3, this is still not solved. And the beta equal to 2 case is this recent paper I did with Pierre Nolin, Wei Qi, and my student Zizhe Zhuang. So we show that this exponent is the unique solution to this simple equation in this interval. And then using some not very hard transcendental number theory, we can see that this exponent is actually a transcendental number, and the numerical value is this. And so there's no prediction in physics other than this wrong guess. So what happened is that since all the known exponents for percolation before this exponent is rational numbers, so the physicists naturally guessed that this exponent should also be rational. And by that time, they can only get the simulation up to this point, up to the second digit, and then this was the closest rational number to this value. But then later, there are some other physicists, actually some Chinese physicists, they were able to get the number to the fourth digit, which contradict this prediction. But even at that time in physics community, there was a opinion that maybe the physics simulation was wrong. So, but our work shows that this Chinese physicist group, they are actually doing a great job to getting this numerical work done. Okay, and so one thing I want to emphasize is that the standard application of the KBZ relation, which I used to derive the one-arm exponent, would be hard to work here because, as I mentioned, this KBZ relation is a quadratic relation, which means it is algebraic. And then post priori, we know that beta 2 is a transcendental number. It means that even this quantum exponent, which was simple in the one-arm exponent case, it would be a transcendental number even in the quantum case. Which means that, okay, so we can definitely use this philosophy to reduce this problem into some counting problem on random triangulation, but the exponent would still be a transcendental number. And I think this means that the enumeration problem would be hard. And our proof, it relies on this analog of the DUZZ formula. So DUZZ formula is a three-point correlation on the sphere. And our proof uses the three-point correlation function on the disk. And then by combining the, so I would not have time to explain the proof of this, but you can imagine that by combining the proof method of this and the proof method of the crossing formula on the one-arm case and the polar chromatic two-arm case, we can also get the annulus formula, the exact annulus crossing formula of this event B2. And this formula looks like follows. So so here, this is an expansion in this modular parameter. And the first, okay, so modular some linear transformation. So the first number is just this backbone exponent. And then all the subleading powers here, they are actually the solution to this equation. So basically, this formula gives some physics explanation of all the other roots in this equation after some linear transformation. And again, this was also not predicted in physics. And this is proved using this, combining this method to derive the exponent and also the method of deriving the random moduli. And again, this is not easy to use to derive using the enumeration planar maps. And it relies on the boundary analog of this DUZZ formula. Okay, so, and here are some outlook. So one thing is that so far, the random moduli question for the Brownian surface, it has only been solved on annulus case. So, which means that for Brownian surface, we have a complete CFT description of Liouville quantum gravity only in these three surfaces. And but there is a general conjecture for heterogeneous surfaces in terms of the where Peterson measure and this ghost CFT. So in some ongoing work, we are hoping to address this problem in a more general surface. And another interesting question would be to understand this full, this CFT behind percolation. So we know that, so even just with some very high level understanding, Cardi was able to use the CFT to predict the Cardi formula. But there are actually like richer connections. For example, like one nice question would be rigorously making sense of this mysterious method called Coulomb gas. And there's another interesting connection to the imaginary version of Liouville theory. So in a recent paper, we showed that this three-point function on percolation, which describes the probability that you have three planar points connected by a percolation cluster. So this probability after renormalization, this will be described by the imaginary version of the DUZZ formula, which is you replace the gamma parameter in the Liouville CFT by imaginary number. And this, by the way, this was already predicted in physics, but to this day, the precise connection between this imaginary Liouville theory and the percolation is still mysterious. And another interesting question is to understand the CFT interpretation of this backbone exponent and this annulus crossing formula. So, so one thing I didn't mention is that, okay, so in this Q parameter, we can expand this annulus formula in this way. And then there's also a dual modular parameter, which is given by e to the 1 over tau. And if we use the, if we expand this probability in the e to the 1 over tau parameter, then the expansion is also pretty nice. And this suggests that this probably is some partition function of a CFT because of this nice modular property. And this would mean that this CFT have a pretty interesting spectrum. But this is to be understood. And the hope is that if we can see this CFT interpretation, and then we would be able to also get the beta j for j bigger than 3, which is currently open. And then finally, I want to mention that all the applications so far and all the questions ahead, they can also be applied to other lattice models. For example, even for the simplest one, the random walk, there are some unsolved questions. Okay, thank you very much.
Okay, thank you for a very interesting talk. Are there any questions from the audience?
Yeah, I have 2 questions. The first one is, are there any other percolation formulas that you would want to derive other than beta j?
Other formulas?
Yeah, other percolation ones?
Okay, so for example, so here we derive the 3-point function. The 3-point function is you have 3 points on the plane. What's the probability the 3 points are connected? This is the problem, and this is given by the imaginary DUZ formula. What I have the hope is to derive the 4-point function, and this will be a function of the crossing ratio between the 4 points, and this would have some conformal bootstrap formula. Okay. So finally, I would imagine that percolation would be as solvable as Liouville theory, but this is like a so far dream and more.
Okay. Yeah, and then the second one is, what are the unknown formulas for random walk that you alluded to?
Okay, so there's one question. Okay, so one formula would be one formula is let's consider a annulus. Okay, and then what's the probability that I can have a random walk that connecting the 2 boundary without disconnecting the boundary? So connecting the 2 boundary without doing these windings. This is the so-called disconnection probability. And then, so Lawler, Schramm, Werner, they show that this leading asymptotic is given by like 1/4, I think, something like something related to 1/4. But the exact formula was not known. And in an upcoming work with some of my students, we have an exact formula for this. This is one example of something which I think in the literature is not known about the random walk. Okay. And then you can also consider extension to random walk, this so-called Brownian loop soup. Then I think, so my understanding is that the self-folding walk, it can be viewed as a degenerate version of conformal loop ensemble. And the random walk can be viewed as a degenerate version of the Brownian loop soup. And if you go to the Brownian loop soup, there are even more formulas you can compute.
Okay, thank you.
Are there any other questions? Very naive question. It's not my area, but asking as a algebraic geometer. Is there a reason behind this formula of beta 2 that you had that this was not, this is a transcendental? Yeah. Is there some sort of implication that this is transcendental or that this?
I think the implication, I mean, to me, one of the practical implication is just nowadays in percolation, people don't believe the exponent should be rational. At least, so actually later we compute some other exponent in percolation, which are also transcendental. It's like, it's equally likely to be transcendental or not. And this also means that the numerical simulation might not be very helpful in these cases.
Is this formula easy to derive?
Not so easy. I mean, so I think, if you go to Remy Rose's talk, you will see this DUZD formula. this is not the most simple formula, to say the least. I mean, but so basically, yeah. So in many other cases, since we know there's a conjecture we want to prove, so once we have some complicated formula, then we can see that okay, eventually we need to match with this conjecture formula. So we have a goal to prove. But here, since there's no physical derivation, so we have to really simplify the arguments, and yeah, so then we were able to find this.
Any more questions?
I think you are pursuing some exact formula, and is there any possibility that there is an exact formula, but it's too complicated, and you can actually, even if you have the explicit expression, you can have little information about it. Is that possible?
I think nowadays, if you have an exact formula, usually you can, at least if you just care about exponent, then if you have an exact formula, no matter how complicated it is, as long as it is exact, this means you should be able to extract the numerical value out of it. But I agree that if you're computing some quantity, which is like you have a formula for some like more general geometric observables, it is possible that even having exact formula doesn't matter. Doesn't help. And I think I think the main point of computing exact formula is not to computing the formulas, it's mainly to discover the structures. For example, you can see that here there might be some Virasoro algebra behind, and we want to find the representation theory for this algebra. So this is and the exact formula is like usually is the tip of iceberg. So it's kind of that the fact that you can prove this exact formula means that there are some deeper algebraic reason behind.
Thank you.
Any more questions? Well, if not, then
That's okay. I can ask.
let's thank the speaker again.